Hey guys, in this video I'm going to show you guys how we actually go about drawing ions in the form of the Bohr diagram, which we've previously looked at, about drawing atoms, and hopefully a nice easy way for you guys to do it, or a consistent way, so no matter what element you're given, you can go through the same steps and you'll end up with the correct answer. So we're going to be doing a practice one for the element here. Sodium. Nah. So, again, with a Bohr diagram, the first thing that we always do is we draw the nucleus, which is a center circle. And inside our nucleus, we always have the protons and the neutrons. Now, with sodium, it looks like, ooh, squeezy time again. I think that's 23. Alright, cool. Again, just having a look at the periodic table at the back. So there is, the atomic number for sodium is 12. So 12. And then just doing some quick maths in my head, the weight's 22.99, minus that round up, so it is 13. Now, because there's 12 protons, we need to have, no there's not, it's 11, Mr. McQuaid. That's dumb. Make sure you're not like Mr. McQuaid and get the wrong numbers. 11. That one's 12. Thinking too far ahead. Alright, so we have 11 protons, which means we have 11 electrons. So the first thing we do is we draw our first shell. How many can we have in this first shell? That's right, 2. So we have 1, 2, which now leaves us with 9 electrons. So we still need to draw another shell. So we draw another shell. Second old circle, and this one can only have 8, so we draw our 8. 1, 2, 3, 4, 5, 6, 7, 8, which means we have 1 electron left over. So we draw that. We need to draw a whole new shell, and we just need the 1. Alright, so hopefully that wasn't, you guys should see this and be like, oh yes, this thing's really, I know this one, done heap of them, good job. Yeah, this is the Bohr diagram for sodium. Now, what we're going to do is we are going to then, something's happened, and it wants to become an ion, so it's nice and stable. So the first thing I always like to do is I rewrite the symbol. Because the protons and the neutrons are not changing, it is still going to be a molecule of, it's still going to be sodium. So you write Na. Alright, and there's always still going to be a nucleus, and this has not changed. So P is still going to be 11, and N is still going to be 12. Nice and easy, right? Now, as we were talking or looking at in the last little section, the molecule always wants to use the least amount of energy to become stable. So with this one here, sodium can either fill its outer shell with another 7 electrons to make 8, or it can lose 1 electron to drop down 1 and have a full outer shell. So it's easier to lose the 1. So here I have a little minus symbol. And what I like to do is that I draw a little arrow coming off, saying that to become this ion, you need to lose an electron. And how many electrons have we lost? We've lost 1 electron. So to become the ion, which we're going to be drawing here, you need to lose an electron. Alright? So, now we've lost that electron, we should have 10 electrons to play with. So we've got the first shell, which has 1, 2, easy enough. We now have 8 electrons left. We draw another circle. 1, 2, 3, 4, 5, 6, 7, 8. Now, are we done? Not quite. We're almost done, but we just need to add one little thing on just to indicate that we've actually drawn an ion. So by losing this negative charge, we've upset that balance of electrons and protons. We now have more protons than we do electrons. So protons have the positive charge, which means that total, we've got 10 electrons and we have 11 protons, which means we have a positive charge, because we have more protons, of 1. So to indicate that we know this is now an ion of sodium, we write the charge up above. So we write it here, plus 1. Or plus, if you want to be super specific, 1 like that. Now you can't write it next to it, because that's just sodium plus the number 1. You need to write it as a superscript, or the floaty number, kind of like my C is in my name. And that indicates that this sodium molecule, this sodium atom, now is an ion, and it has a positive 1 charge. So, we're going to...
Wow, I just teleported from there to here, and the board is clean. Is it magic? I think it is.
I'm having too much fun with this. So now we're going to do another one. Get rid of this. Whoopsie daisy. We're going to be doing another one, and we're going to have a look at a different element this time. So here I've got the symbol. I haven't just gone... I've got the symbol for this element, which is indeed O, which is the element oxygen. So oxygen has an atomic number of 8, just again check in the back there, and a weight of roughly about 16. So again, every board diagram, first thing we do, it's going to get tiring for you to listen to it all the time, but there's a reason why I say it every time. In the middle we have our nucleus, where the protons and the neutrons are stored / live. So 8, and if it's got a weight of 16, 16 minus the number of protons, 8 is 8. 8. I might be wrong there. Anyway, so if we have 8 protons, how many electrons do we have? 8. So if we draw our first shell, how many can you fit in this first shell? 2. 1, 2. That means we have 6 left over, which means we now need to have a second shell. 1, 2, 3, 4, 5, 6. Awesome. So this is the board diagram for oxygen. Is this stable? No. Because if it was to be stable, it needs a full outer shell. So with this one here, this is the last outer shell. So we can either complete it or get rid of it. So we can either complete it by adding 2 more electrons, or we can get rid of it by removing 6 electrons. Now again, remember energy efficiency, it's going to be easier to gain 2 electrons. So what we do, as per usual, if we've got this kind of setup, we write the symbol again underneath. I'm going to jump over here. We write O, and we do this again. So this time, I forgot to rub this off, but to complete this outer shell of oxygen, we are gaining electrons this time. So what I like to do is I draw an arrow going up and in, just to indicate that instead of being removed, we're now adding electrons, and we're adding 2. We put the number 2 there. We have 2 negative electrons being added on. And now we just draw it like we normally would. So again, the nucleus, P, N, 8 and 8. 1, 2. 1, 2, 3, 4, 5, 6. But instead this time we have, let's get close, we have 2 extra electrons. So now we've got an imbalance between the protons and electrons. But this time we have 2 more electrons than we do protons. Which means, since the electrons are negative, we have 2 more, or a larger electrical charge by 2, so negative charge by 2, than we do positive. So overall, it is now a negative 2 charge, because we have 2 more electrons. And again, we just need to notify this on the symbol. So we write it in the top right hand corner. So we always write it up here, and because we've added the 2 and we've added them, it kind of doesn't make sense that it is now a negative 2. But that's the charge of the electrons. You've added 2 extra, which means you have 2 more negative things, which means it is now a negative 2 charge. Which means now that is complete use. So you know when there's oxygen, it has a negative 2 charge. Which if you either look at your periodic table or watch that other video with the periodic table drawing here, you would have seen that oxygen does indeed have a negative 2 charge and everything else in that row. So again, if you are good with that, please continue on with the questions down below. If you want to recap it, both looking at an extra proton or extra electrons, just grab the little Duvallaki from here. Let's go back to the start and rewatch this whole thing. But if you're all good, I'll catch you in the next episode. Yeah, never know what to do with the end of this.